Okay? Item B, intrinsic geometry, exterior algebra in 3D or 2D, 4D, 4 dimensions, see, any dimension. Now, B part 1, manifold. B part 1, lecture 14, transition function, numerical example. As I pointed out in the previous lecture 13. Now, give a point P, 1, 2, belongs to the manifold, okay, two-dimensional manifold, M2. Now, also, assuming, consider the linear mappings, alpha sub x, this is a 2 by 2 matrix, alpha sub y, this is 2 by 2 matrix. Okay, I choose this particular case of the matrix because they represent an orthonormal system, you see? And then if I multiply alpha sub x times the inverse, this leads to this case, okay? The diagonal, okay, we call this case 1, 1, and 0, okay? This identity matrix called I, capital I, you see over here. Likewise, I choose this mapping just such that the inverse of alpha minus 1, in this case, okay, this here also is an identity matrix, okay? Identity matrix. Since these represent orthonormal bases, you see, consequently, the inverse is equal to the transpose, okay? The inverse is equal to transpose. That's a property of linear algebra. Now, step 1, that's marked right here. Step 1, transforming the point P, 1, 2, using this linear map over here, okay? So x1, x2, attention now, x1, x2, they are coordinates, local coordinates to the manifold. That's a point P. To map this Cartesian coordinate using alpha x, you see, it's interesting. I will repeat and I will insist. Although 1, 2 belongs to the manifold, this point is represented in Cartesian coordinates. So Euclidean coordinates, 1, 2. This is a curved surface, okay? But locally, this I represent each point using the Cartesian coordinate, you see? So then I will apply this map here to the point x1, x2. You see this a matrix, this is 1, 2, and this leads to the two components, okay? Components, phi1 and phi2, just this. This is Cartesian space, okay? Phi1, phi2. You just multiply, and then I get the components, phi1 and phi2. This is 3 square root of 2 divided by 2, square root of 2 divided by 2. That I call point Q, the same notation as we used in the previous lecture. Now, step 2. Apply this linear operator, attention now, to obtain this Cartesian components, C1 and C2. The analogous that we did for alpha sub x, I will do for alpha sub y. You see, I just copy from here and I repeat over here. See, this applied to the the point P1, 2 is the same point. You see? This I will get the point Q prime. Attention now. Attention now. The point is invariant. We can represent the point using any system of what? See, actually, the components of the same point, when I use one system, I call Q. Q, the point is not different from Q prime. Attention now. This point is in the same location, but the components, they are different, okay? For instance, when you have a spherical, okay, a point in a spherical surface, you can represent this point using the coordinates r, you see, phi and theta. You say the position vector, okay, is the same when we use Cartesian coordinates, you see, because point is invariant, vector is invariant. What means invariant? It don't depend, okay, when I substitute a coordinate system by another, you see? So I just here, I'm going to call your attention that Q here is related to one coordinate system called phi1 and phi2. And Q prime is the same point. Then is represented, okay, in another coordinate system, psi1 and psi2. I think it's clear when I emphasize the concept of invariant. Now, step 3. Since the point is invariant, I can relate in this case, this coordinate to this one, okay? Now, this y1, y2 is a coordinate of points on the manifold, okay, which are represented by the coordinate system over here. The x1, x2 is a system, okay? Then when I move to another point, I represent to y1, y2. But in this case, the point is the same. Point P belongs to the two systems. Okay, that's important here. Now, important concept. The point P1, 2 is invariant. You see the word, this is a magic word. Likewise, the mapped Q and Q prime represent the same Cartesian point, since the orange is the point P. Point P leads to coordinates, which is a point. That's I call Q, okay, and the same point. Now, in different coordinates is Q prime. The orange is a point P. I applied in the same point P two different mappings. See, that's to be clear. And this is clear. See, when I map this phi1 and phi2, okay, this leads to point Q, and psi1, psi2 lead to the same point, which I call Q prime. Keep this in mind, please. Then you see, this point here, Q, is identical to Q prime, although the coordinates are different. Like I said, Cartesian coordinate and spherical coordinates, okay, can be represented can be used, okay, to represent the same point, okay. Now, this is clear that, you see here, now, this is x1, x2. Attention now, alpha sub I, y1, y2. Attention now. This is transformed, okay, to a system, in this case, okay, by this linear operator here. And from there, at that point, I bring back to the same point P throughout the alpha x minus 1. You see, look how interesting. Alpha sub I take a point, for instance, in a manifold, and send to another system, alpha, which is a point. Alpha sub x minus 1, the inverse, or is equal to the transpose, in this particular case, bring back the point to x1, x2. So I can calculate, you see, this product, okay? Alpha x minus 1, alpha y. I just get, I call this the operator M, y. M here, attention now, it will appear over here. So that's it's good to emphasize. So this over here is M. See, I calculate, already calculate this. So x1, x2 is M, y1, y2. This is M here, y1, y2. Again, I'll repeat the same figure that it was displayed in lecture 13. See, this over here, okay, this is attention now, this is a point Q, attention here. This point Q is located on the same place of this Q prime, okay, but the component, the coordinates, they are different, but the point is the same. Attention now, because the origin was